time schedule. Today I will talk about my recent work on the combinatorics related to finite classical groups. So the talk is divided into 4 parts. In the first part, I will talk about some basic notions and facts about finite classical groups. And in the second part, I will apply the facts in the first part to study highly transitive geometric structures and subgroups of with classical groups with few orbits. In the third part, I will give an overview of the application of classical groups in at the different levels of symmetry in finite geometry. And in the fourth part, I will talk about when group theory does not work, how to introduce algebraic method to solve problems. So first, we start with the classification of finite simple groups. A finite simple group is one of the following, which is a cyclic group of prime order, an alternative group, a simple group of Lie type, and 26 sporadic simple groups. Our concern will be the third class, which is the groups of Lie type, which includes the classical ones and the exceptional ones. So around 1960, Jacques Dietz developed building theory to study semi-simple Lie groups from a geometric viewpoint. So he is the first one that emphasized the importance between the interplay between geometry and groups. So for spherical buildings of rank at least 3, they classified them as projective geometries and polar spaces. And their automorphism group are the classical groups. So the middle column is the geometry, and the last column is the group. But when rank is 2, it's also called generalized polygons. And the automorphism group of classical generalized polygons are Lie groups of Lie type. So, but there are a lot of there are non-classical generalized polygons. Okay, we will briefly explain what is the classical groups and how to define the related polar space and the group. Let beta be a reflexive, non-degenerate sesquilinear form or vector space. So there are actually symmetric bilinear form, alternating form, or the emission forms. So there are only 3 types. We can define a subspace to be totally isotropic according to whether any 2 vector of u are perpendicular or not. In this way, we can define a polarity, which is a bijection between projective points and hyperplanes. So that preserves instance. The polar space associated to beta is the geometry. When we talk about geometry, we need to have objects of different types. So point is the one-dimensional, totally isotropic point. And the lines are 2-dimensional, totally isotropic vector spaces. And the planes are 3-dimensional, totally singular subspaces. So their type is their dimension. There's a natural instance between them, which is by inclusion. So we have objects of different types and instance relations between objects from different types. This is the geometry. So we have objects and incidents. Okay, one of the most useful fact is so-called Witt's lemma. It says a asymmetry between subspecies extends to a asymmetry of the whole space. So it's very helpful, very, very helpful, useful. As a corollary, all the maximal totally isotropic subspecies of a polar space have the same dimension called the rank of the polar space. So the rank is also the number of types in the geometry. So the finite classical polar spaces of rank R are listed here. So according to the type of the form beta mentioned earlier, which is symplectic, unitary, and orthogonal. There are 3 orthogonal types. Okay, find some related combinatorial objects. We define, starting from a classical polar space, we define its collinearity graph as follows. So its vertex set are the points, which is the isotropic or singular points. We use the term singular in the case of a cortiform. Okay, so we see 2 points are adjacent if and only if they are perpendicular. It is a strongly irregular graph, which is a simple corollary of Witt's lemma. A vertex set of this collinearity graph gamma is a regular set, which is also known as intriguing set, if and only if the hyperplanes intersect the set M in 2 sizes, according to P is in the set or not. There are 2 types, which is the I-type set and M ovoid. This will be, the reason is from this geometric property, which is about intersection sizes, it translates to eigenvectors of the collinearity, the adjacency graph, adjacency matrix of the collinearity graph gamma. They correspond to different restricted eigenvalues. By restricted, we mean you just simply exclude the valency. Okay. An I-type set and M ovoid intersect in M times I points. This is a simple corollary of the fact that eigenvectors of distinct eigenvalues are orthogonal. We will come to these objects later. So next we talk about some basic facts we use about classical groups. So first, certainly we have the classification of finite simple groups. The second is the structural theorem of their maximal subgroups. And the third is the determination of their low-dimensional representations and the low-degree permutation representations. All these facts, all these are known. So you simply need to know where to find them, right? So first, the subgroup structure of classical groups. In 1984, Eschbach classified the subgroups of classical groups into 8 geometric classes, C1 to C8, and 1 non-geometric class. Basically, you throw the ones that does not fit into the first 8 classes into a trash bin, which is we call class S. So C1 to C8 are called geometric classes because they are defined in a geometric way. For instance, the first is the stabilizers of subspecies. Second is the stabilizer of a certain subspecies direct sum decomposition. So we mentioned the difficult part, the Eschbach class S. It is closely related to the representation of finite simple groups. For classical groups in the defining characteristic, they can be derived from those of the associated linear algebra groups, which require the knowledge of a root system and V modules. The Sternberger tensor product theorem would tell you a irreducible module is the tensor product of p-restricted irreducible modules. And in the cross-characteristic case, there's a large lower bound of the dimension of such a representation. So these are some standard references on classical groups. So this will allow you to understand the basic facts. And for the low-dimensional representations, there are published references. So simply quote them. And to mention the last one is the Atlas of finite groups. There is an online version, so you can find an online database that includes thousands of specific representations. Okay, those are the facts that we will use about classical groups. So the second part, we will talk about applications to groups. So first, what are the classical groups? We mentioned the polar space. So what are the groups? The groups, to put it in the simple way, it's the asymmetric group. Okay, this is a invertible linear transformation which preserves the form. I use the quadratic form as a demonstration. You can define this for the symmetric case, symplectic case, and the omission case in a similar fashion. So the other subgroups are variations of the asymmetric group. So you have the semi-similarity group, you have the asymmetric group, the special asymmetric group, and a certain omega. It is of interest in the orthogonal case. You need to be very careful. It's more or less the derived subgroup of the special asymmetric group. So when we talk about the simple groups, we are actually talking about their quotients, which you modulo the center. Omega, p omega is usually the simple group. So in the study of simple groups of H-bar class, subgroups of H-bar class S, we actually start from a group G and examine its finitely generated absolutely irreducible module. We classify such irreducible modules, then we determine its Frobenius Schrödinger indicator, which is circle plus or minus, according to whether it's self-dual or not. If it's self-dual, then there will be a non-degenerate bilinear form that is preserved by J. And so the plus case would tell you whether there's further a quadratic form. And the minus would be the remaining cases, the alternating case, alternating form. So after determining the Frobenius Schrödinger indicator, you will find that G will embed into the corresponding classical groups defined on M and the corresponding G invariant form. The case where the Frobenius Schrödinger indicator is a circle, where it's not self-dual, it could be quasi-equivalent to its dual. So you have the unitary case. For the unitary case, we have such a useful criteria. So we first determine the character ring of the representation. In most cases, they are generated by quadratic irrationalities, which are algebraic integers, which are algebraic of degree 2 over Q. So this lemma will tell you when the representation have a unitary form. So as a application, we classify the M voids of a finite classical polar species that admit a transitive automorphism group acting irreducibly on the ambient vector space. And then last year, we classified the subgroups of similarities of finite classical subpolar species with exactly two orbits on the singular or isotropic points. As a byproduct, we obtain many highly symmetric intriguing sets of so known as regular sets. Both results make essential use of the above techniques, so they are long. You need to go over the list of all the classical, the simple groups and their subgroups. So here's a brief overview of our results. So we will focus on the H-bar class S. So in this such a case, the subgroup is written as H. H, there's a simple group L such that H is between L and M, where L is the circle and M is the normalizer of L in the four largest similarity group. These are the M voids that admit a transitive subgroup. There's a subgroup H. So one of the H orbit is a M void. These are the list. We rediscover many of these well-known ovoids. So for the subgroups of finite classical groups with exactly two orbits, we also mention examples from class S only. So this is the tight sets. So we find that there are quite several examples with high dimensional cases. For instance, in the last column, we have a 25-dimensional module which have the F4, one of the exceptional groups of Lie-type as an automorphism group. This is a minimal module of F4. And the second from the bottom, which is Q plus 15Q, it is the spin module of span Q. This is this come from very detailed calculations involving the spanners. So our analysis of the class S comes from a very detailed analysis of the following cases. So because for the high dimensional cases, we can simply use parameter considerations to exclude them. Those cases where the parameter restriction is satisfied, you need to go over the list one by one, and so you need to know the structure of the module, and you need to work explicitly with the form, and show that either there are more than two orbits or there are exactly two orbits. So this is the intriguing part of such type of problems. There's no unified approach to all the cases. You need to go over all the cases one by one. Okay, these are so we will come to a overview of applications of finite classical groups in the study of finite geometry, in the sense of the degree of symmetry they demonstrate. Roughly speaking, there are three aspects of finite geometry, which we call analytic. Analytic geometry, which is the study of geometry by using equations. And the second is transformation geometry, which studies geometry from the viewpoint of the symmetries they have. And the third is synthetic geometry. So you study geometry starting from some axioms and try to study their properties and do classification. From a Kleinian viewpoint, the interesting geometric structures are usually associated with interesting groups. From a geometric perspective, the interesting geometric structures usually exhibit certain regularity. So we study finite geometric structures that satisfy certain regulatory conditions and exhibit high symmetries. For instance, projective planes. A projective plane of order n is a point line instance structure that satisfies the following regularity conditions. So first, we have two different types of objects, which are respectively called points and lines. So those are the regularity conditions, which I will not read here. The fourth one is called non-degeneracy. So it avoids the degenerate cases. So there are 4 points that are not collinear. Alternatively, its point line instance graph is a regular bipartite graph that has diameter 3 and girth 6. Later, we will see a generalization, which is the generalized polygons. So finite projective plane is a generalized triangle. According to the symmetries geometric structure exhibits, there are roughly 3 cases. So highly symmetric, moderately symmetric, and barely symmetric. So highly symmetric, for instance, you have an assumption such as flag transitive. What is a flag? It's an instant point line pair. It's called a flag. So flag transitive means transitive on the set of all flags. Other include the permutivity on points, so point permutive. So it's the weaker assumption would include point regular. So there's a group that is regular on the points, that is transitive on points, and the stabilizer of each point is 1. So we consider these 3 cases separately. For the highly transitive case, the classification of finite geometric structures that satisfy certain transitivity assumption is a mainstay in finite geometry. It has a long history. So the first such result is 1959 due to Ostrom-Wagner, which claimed that a finite projective plane having a 2-transitive collinearity group must be transitive. So the group is 2-transitive on the points. Such a projective plane must be classical, which is also known as de Saxen. As far as classification is concerned, the solvable case seems more difficult where the problem reduces to arithmetic or algebraic one, and the group theoretical tools no longer work. So you first apply group theory, and there will be some loose end where it's no longer a group theoretical problem. In the last part of this talk, we will see such an example. So we need to introduce method in algebra. In 1987, Cantor showed that a point primitive projective plane of order n is either de Saxen or it satisfies that n squared plus 1 plus 1 plus n plus 1 is a prime. In the latter case, the group is a Frobenius group. It is a very long-standing conjecture that the last case does not occur. Yeah, it's very difficult. I thought about this problem, but I did not make progress. Okay, some easy ones. We mentioned M ovoids. Ovoids are simply one ovoid. This is a demonstration of the stream of study concerning finite geometric structures. So, assuming that there's a group that is transitive on such a ovoid, then we can, the final solution is in 2021 by me and my former PhD student, Wei Tong Li. So we see that in 2003 they classified. So the difficult part is the solvable case. So in 2003, Costantini and Koshmaros classified the linearly transitive ovoids, which are subgroup. So the 3 is the non-solvable case. 4 is the solvable case. And Morehouse and first and second does not make assumptions on the transitivity. The good thing about the non-solvable case is you have the rich theory we mentioned earlier to do analysis. But in the solvable case, we need to use closed-mind sum estimates. So it's a bit surprise, right? You need to use such exponential sum calculations. So finally, this is the result. 4 and 5, the last two come from our analysis. Okay, here is a recent result. In the study of factorization of finite classical groups with a solvable factor, we use geometric arguments to deal with unipotent radicals. This allows us to determine an explicit list of classical groups with such a factorization and give explicit descriptions of possible factorizations. This problem is a purely group theoretic problem, and they cannot solve it by using purely group theoretic arguments. So by using geometric arguments, we are able to give a complete solution. So this is posted on arXiv a few days ago, and we get pretty positive comments from group theorists working on this field. So we can use group theory to work for geometry, and we can also use geometry for groups to solve problems where purely group theoretical arguments cannot work. So yeah, it's I'm happy with such a type of results. So in the case of a moderately transitive, you don't do classifications because there's no point. You do constructions. You try to construct interesting geometric structures. So by combining the subgroup structure of classical groups and using complicated exponential sum calculations, we have done systematic work on the classification of geometric configurations with a solvable automorphism group. Solvable usually small, so the group order is small. We prescribe a particular solvable automorphism group and construct some interesting geometric structures. This includes the first family of Cameron-Lieber line classes in the even characteristic. Finally, in the Bailey symmetric case. Heuristically, almost all finite geometric structures do not exhibit any symmetry. So it's known that almost all graphs have no symmetry. This is a very standard fact in graph theory. So in such a case, group theory fails to feel pre-schematic, and geometric analysis takes over. So you need to do ad hoc geometric analysis. So one of the most famous conjectures is that there's no ovoid or spread in finite classical polar spaces of high rank. So this is very interesting. So you cannot use group theory. So this is not our main thing here in this talk. Okay, finally, I talk about some applications of algebra, introducing algebra into the study of finite geometry and combinatorics, where group theory does not work. So we start with the basic definition of instance structure. Geometry is a certain kind of instance structure. It's a fairly simple definition. So you have two different types of objects, which are the points and the lines. A instance structure is simply a non-empty subset of their Cartesian product. So it's fairly simple. Of course, not all instance structures are interesting. So we need to make assumptions on the regularity. So for a point P and a line, if PL is in the set I, we will see that they are a flag. We also write P tilde L to mean that they are instant. Otherwise, it's called an anti-flag. So we mentioned the flag transitive earlier. The instance graph of this instance structure I is the bipartite graph whose two paths, P and L, it has two paths, which is P and L. A point is adjacent to a line if and only if they are instant. So here comes the generalized polygon, which is my personal favorite. So a generalized n-gon is point line instance structure, whose instance graph has diameter n and girth 2n. We mentioned earlier that these are the polar space. These are the rank 2 buildings. So there are some degenerate cases. So we make two further assumptions where each point is on exactly t plus 1 lines, and each line has exactly s plus 1 points. In such a case, we call such a generalized polygon to have order s and t. It's thick if both s and t are greater than 1. So a very famous theorem of Fichte-Hagemann says if S is a thick generalized polygon, then N is either 2, 3, 4, 6, or 8. The proof uses the theory of a distance regular graph. So if you drop the thick condition, you will have 12. When N is equal to 2, you have the complete bipartite graph. When you have N equals 3, you have the generalized triangles, which are the projective planes. So N equals 3, we have the projective planes. And N equal to 4, we have the generalized quadrangles. And equals 6, have hexagons. 8 is octagon. So on the right-hand side, we list some examples, the classical examples. So the classical projective planes are PG to Q, and the classical GQs are the rank 2 polar spaces. And the hexagons are related to the classical groups G2Q and 3D4. And the octagons have to do with the group F4. So they are associated with the classical groups and exceptional groups of Lie type. Later, we will focus on generalized quadrangles for the remaining part for the final result. So this is a recapitulation of its definition. So fairly simple, three conditions. When S is equal to T, we see that it has order 3S. The third condition, you can, in the simple way, the third condition says a GQ has no triangles, so ordinary triangle. So the third one is equivalent to that. It has no triangles. That is, its instance graph have diameter 4 and girth 8. So 3 is there's no triangles, ordinary triangles. These are the classical examples. So the circle of their automorphism group are the simple groups are these simple groups. And the right-hand side, we list the parameters. An automorphism consists of two permutations. One is permutation of points. The other is the permutation of lines. I will not, that preserves the instance. So this is automorphism. I will not explain the remaining definitions due to time limit. So for the classical generalized polygons, the automorphism is transitive on flags and primitive on both points and lines. The classification of flag transitive generalized polygons is listed as one of the 10 most famous problems in the appendix of Van Manderheim's book with the same title, Generalized Polygons. So one of the most studied conjecture is about generalized quadrangles, which claims that a flag transitive generalized quadrangle is either classical or two sporadic examples. So these are the some of the recent work, and we have done something in this direction. So the last result we are mentioning here is about elation GQs. So I will now explain what is elation GQ. Simply a sort of GQ that have 13 type of automorphism group. You will simply skip these notions. Okay, we choose some points and lines and define AI and AI star as their stabilizers in the automorphism group. Then we will have these two conditions, K1 and K2. K is after counter. So if we have such subgroups that satisfies K1 and K2, then we can do the opposite. We can reconstruct the GQ. So we call these subgroups the orthogonal families associated with the general quadrangle S. So if this AI star intersects in the intersection of these AI stars is as large as possible, which is of order F, then it's called a skew translation GQ. This notion is coined by Stampen in 1975. So these are there's some properties where it's known that F is a power over 2. In the same paper where he introduced the notion, of skill translation general quadrangle, he conjectured that the elation group, the automorphism group G, must be elementary abelian. Out established the conjecture for S and odd power of 2 in 2022. So there are 4 main steps. It's purely group theoretical. It's very, very simply group theory. The condition on S, which requires S to be an odd power over 2, is only used in the second step. So what I did is find an alternative proof of the second step without restriction on S. So it works on all powers of 2. This is done by defining a 4-dimensional commutative algebra from the associated four-gunner family and use character theory. So this completes the proof of Payne's 1975 conjecture. In the same paper, by using a bit extremal graph theory and the theory of solvable linear groups, we are able to establish the following result. So there's no general quadrangle of even order with a point regular automorphism group. So the group is small because it's regular on the points. Regular means transitive, and the stabilizer of one point is trivial. This confirms a 1992 conjecture of Ginelli, and the proof uses a little bit of extremal graph theory, actually, expander mixing lemma, and the theory of solvable linear groups. The solvable linear groups is studied in Superninko's book in 1972. So 5 before the classification is done. So actually, my original proof make use of the Eschbacher list, C1 to C8 and type S. So it's long. And Bill Counter told me that in your case, your group is solvable. So don't do that. You can quote Superninko. So it reduces to the original 4 to 5 pages to 1 page. Okay, this also confirms 2018 conjecture of Eric Sohns. Okay, that's all. Thank you.
So, any questions? Okay. So those of you that are just coming in, the 2 speakers this afternoon agreed with one of the speakers whose lecture was canceled yesterday to split the 2 hours into 3 45-minute pieces.